The bisection method. This is the most robust, but probably least efficient of the root finding methods. We will start by just describing the method with illustrations and end with some notes on how to implement it. Description of the method. So we have a root somewhere that's basically unknown, and we need to define bounds somehow magically that we know span this root. And as I mentioned before, we talked a little bit about this. We could plot the function. Maybe there's something about the physics of the problem that lets us know around where that root is, but somehow we have to be able to determine bounds that span a single root. If we can't do that, then this method will fail. So let's say that's where we start. That's step one. Step two, and this is why it's called the bisection method, we're going to bisect the bounds, and we're going to calculate a guess at the root, and we'll guess that it is exactly midway between the two bounds. So we'll just take the x value of the upper and lower bounds, we average them, so sum them, divide by 2, and that's our guess as to where the root might be. And so that lands us right here. Step 3, we will evaluate the function at that point. And remember, evaluating this function might take a week. Have that mentality when you're looking at these algorithms. So we calculate the function at the midpoint. The next step is to adjust the bounds. And we do this by looking at that function value. And I'll admit there's a little bit more to this story that we'll get later, but for now, let's keep it simple. And we will look at the sign of the function. If the sign is positive, where we at our new guess, then clearly the root has to be to the left. And we will take our upper bound and move it to our guess. Now, if that function value were negative, so over here somewhere, then the root would have clearly been to the right. And so we would want to move the lower bound up to our guess at where the root is. But here it's positive. And so we take the upper bound and move it to our guess. And we're sort of back to the beginning again. We have an upper and lower bound. It's narrower. We're starting to close in on the root. And the root is somewhere between these two bounds. We calculate a new midpoint by averaging where the upper and lower bounds are, and our new guess at the root is here. We will then evaluate the function at that midpoint. At this point, we want to adjust our bounds, so we look at the sign of that function. And here the function is negative, so we know the root has to be to the right, so we want to take this lower bound and move it up to where we've guessed at where the root was. So we move the lower bound up. And we're sort of starting from the beginning again, where we have an upper and lower bound, and the root is somewhere in between, but our upper and lower bounds are closing in on that root. We calculate a new midpoint that's now exactly between upper and lower bounds. We evaluate the function at that new midpoint. And we want to adjust the bounds by looking at the sign of the function. The function is negative at our guess for the root. That means the actual root has to be to the right. So we will move our lower bound up to where this guess is. We then evaluate the new midpoint, evaluate the function, adjust the bounds, and we keep repeating all of this. And this goes on for many iterations. It could be anywhere from 5 or 6 to 50 or 60, depending on the tolerance that you want and depending how crazy the function is between those bounds. Notes on implementation. Let's think a bit about adjusting the bounds. And I said when we were going through this that I admitted there's a little bit more to it. Let's think about that. We said if the function value is positive, that has to mean that the root is to the left of that guess. Well, there's another element of information there. That has to be the slope of the function. So if we have a positive value of x, the root is only to the left if the slope is positive. For example, now on the right, we have a slope that is negative. Our function value is negative, but so that means the actual root is still to the left. So in both cases, the root is to the left, even though both cases have opposite sign of the function. So we have to account for the slope of the function in addition to the sign of the function at the new guess. Let's examine how we can do this algorithmically. Is that a word? It is now. So what we will do, we will take the function value evaluated at the lower bound and the function value evaluated at the root. Both of these we should have already evaluated, and we'll multiply those together. And we're not too concerned really about the values. We're concerned with the sign of these. And so if the product of those two is less than 0, then that means these two quantities have to have opposite sign. That means the root must be somewhere between the lower bound and XR. So if this is the case, then we need to make our guess at the root the new upper bound. All right, here's the MATLAB code for doing that. We will look at our function value for the lower bound, multiply that by the function value at the guess at the root, and if that's less than 0, we copy the information over from the root to the upper bound. And the second line of code, there's a bit more to this, so let's talk about that. We are copying the function value at the guess at the root that we've already calculated over to the function value of the upper bound. We're not going to lazily reevaluate the function at this new upper bound. We've already done it. It's the function at the guess at the root. Keep in mind, every call to that function might take a week to calculate. So we don't want to lazily recalculate that. We want to copy our information over to avoid having to call that function. We want to minimize how many times we call that function. Okay, next case. We're going to multiply the function at the lower bound and the function at the guess at our root. If that is greater than 0, that has to mean that these have the same sign. They're either both positive or both negative. In either case, the root is not between the lower bound and the guess at the root. The actual root has to be somewhere between the guess at our root and the upper bound. So in this case, we will move the lower bound up to where I guess at the root is. So in MATLAB, we'll tack on here an else if function at the lower bound times function at the root is greater than 0, so they have the same sign. We copy the information over from the root to the lower bound. And I'll point out again, we're not reevaluating the function at this new lower bound. We've already done that. We just copy that information over, and that has everything to do with speed when calling that function takes a long time. Now we also have to consider, what if the product of the two is 0? What on earth does that mean? Well, that probably means that f was exactly 0 at the guess at that root. We landed exactly on it, and in which case we're going to be done. So in MATLAB, we will put a break command in here to break out of the, we probably have a while loop or something happening outside of that. And so we're done because we found the root exactly. And maybe that almost never happens, but it's going to happen often enough to crash your code once in a while. When is the algorithm finished? What I like to do is calculate each iteration how much the guess at the root changes. So we're calling that a delta XR, and then normalize that. So we'll be calculating a new position for the root. We'll subtract that from the old position of the root, and then divide by really either the old or the new. It doesn't much matter here. We're really essentially normalizing this. For example, if let's say x is a number in meters, and we subtract the 2, and we are 1 meter off, is that good? Is that bad? Well, if we're somehow calculating distance between galaxies, 1 meter is awesome. We're probably done this root finding algorithm. If we're calculating height of people somehow, it's probably bad. So I like to normalize that by really dividing by the values of x that we have. And so it's more of a percent error, I guess, if you will, or a percent change. So we calculate that delta. And then if this delta falls below some tolerance, we'll say that we are done. And what I tend to like to do, if I want 3 digits of precision, I'll set this tolerance down to 4 digits. So if I want 0.001 accuracy, I'll set that tolerance to 0.000, maybe even another 0.1, at least an order of magnitude smaller than the precision that I actually want. Now here's a warning and a easy error to make. So we would never check the tolerance just by the distance between our bounds. And that's because for certain shaped functions, we're only ever moving one of those bounds, and that bound closes in exactly on the root. The other bound could remain very far off and never would move. So if we're just looking at the distance between the bounds, our algorithm, well, I can't say it would never converge. The algorithm will have converged. It's just that our code is not recognizing that it has converged correctly. So don't make that mistake. Let's now step through a block diagram of the bisection method. So we start the algorithm with the function we want to find the root of, and we pick this lower and upper bound that somehow magically we know spans a single root. We then evaluate the function at those points. And keep in mind, keep in the mentality that evaluating that function could take a very, very long time. So we don't want to have to keep redoing that. At this point, we'll calculate a new midpoint. And so it's the exactly midpoint between the two bounds. And this is where we are going to make a guess as to where the root might be. So we'll evaluate the function at that guess at the root. At this point, we're going to enter the main loop. And so we'll multiply the function at the lower bound and the function at the root. And we're really just caring about the signs here. So we'll handle this one case. If that product equals 0, that probably means the function that we've evaluated at the new guess at the root is exactly 0. We're right on it, so we're done. We don't have to continue. If that is less than 0, then we're going to move the upper bound down to where that guess at the root is. And just to remind you, we're copying the function value from the guess at the root to the new upper bound. We're not reevaluating. We don't have to do that, and that could slow our algorithm down if we did that. On the other hand, if that product of the function at the lower bound and the function at the guess at the root is greater than 0, we need to move the lower bound up to where our guess at the root is. And we're copying over that function value, not reevaluating it. So we've moved one of the bounds. We then calculate a new guess at the root. That'll be the midpoint between the bounds, which is why it's called the bisection method, because we keep bisecting the distance between our bounds each iteration. So we'll calculate how much our guess at the root has changed and normalize that. So we'll subtract the position of the new root from the position of the old root from the previous iteration, divided by either the new or the old value. We're normalizing in some way and looking at the sort of percent change each iteration. And that's our delta XR. If that is below some tolerance, we're done. If not, we're going to keep repeating this. And otherwise, we're done. And that's the bisection method. So here is the block diagram in printed form. I'm not going to step through this again, but it's here in print, and some people like this as opposed to the block diagram, so there it is. Some notes we'll end with on the bisection method. As far as I know, this is the most robust root finder. Now, somebody could certainly take a function, do a whole bunch of analysis on it, call different methods and all that, depending on different cases of different things, and probably make a more robust root finder. I'm not talking about that. I'm talking about just the pure method for finding the root. As far as I know, it's the most robust. It's also the least efficient. So we can start doing things to this that make it more efficient, but also maybe tends to make it less robust, and you'll see how that works when we get to those methods. So this method is guaranteed to find a root as long as the bands span a root, and there's an exception to that. What we want to do is verify that there's a sign change on either side of the root. Remember, these bisection methods have problems when there's an even number of multiple roots, and that's because there's no sign change. And so it might be good at the start of this method to check that sign change, and then if there is no sign change, report an error. Or there's that auxiliary function approach that we discussed that we can fix that.